In the vast universe of mathematics, functions are the cosmic architects, shaping and defining relationships between quantities. Simply put, a function is a rule or a correspondence that assigns each input value to exactly one output value. Think of it like a vending machine. You input a code, and it outputs a specific snack. For every input, there's only one possible output. That's the essence of a function. We often represent functions using letters like f, followed by parentheses enclosing the input variable, usually x. So, fx reads f of x. For instance, fx equals x plus 2 means that for any value you plug in for x, the function adds 2 to it. This concept of input and output is fundamental to understanding how functions work. The set of all possible input values is called the domain, while the set of all possible output values is called the range. Mathematicians have a knack for expressing complex ideas in elegant ways. Functions are no exception. They can be represented using formulas, graphs, and tables. A formula, like the one we saw earlier, fx equals x plus 2, provides a clear rule for calculating the output for any given input. Graphs offer a visual representation of the relationship between input and output values. Imagine plotting points on a coordinate plane where the input, or x value, determines the horizontal position, and the output, or y value, determines the vertical position. Connecting these points reveals the shape of the function. Tables, on the other hand, list input values alongside their corresponding output values. While not as visually intuitive as graphs, tables can be useful for organizing and analyzing specific data points. The cosmos is teeming with diverse relationships, and functions are no different. There are various types of functions, each with its own unique characteristics and properties. One common type is the linear function, represented by a straight line on a graph. Linear functions exhibit a constant rate of change, meaning that for every unit increase in the input, the output changes by a fixed amount. Quadratic functions, on the other hand, involve squaring the input variable. Their graphs are parabolic curves, either opening upwards or downwards. Exponential functions involve a constant base raised to a variable exponent, resulting in rapid growth or decay. Understanding different types of functions allows mathematicians to model and analyze a wide range of phenomena, from the trajectory of a rocket to the growth of a population. Section 4. Functions in action, real-world applications. Functions are not confined to the abstract realm of mathematics. They permeate our everyday lives. Consider the simple act of driving a car. The distance you travel is a function of both your speed and the time you spend driving. In economics, supply and demand curves are often modeled using functions, illustrating the relationship between the price of a product and the quantity supplied or demanded. In physics, functions are used to describe the motion of objects, the behavior of waves, and the forces at play in the universe. From predicting the weather to designing bridges, functions are indispensable tools for scientists, engineers, and countless other professionals. Section 5. Conclusion. The significance of functions. As we've explored the world of functions, we've seen how these mathematical objects serve as the building blocks of relationships. They provide a language for describing, analyzing, and predicting the behavior of systems both simple and complex. Understanding functions is essential for grasping the fundamental principles of calculus, which delves into concepts of change and accumulation. Whether we're aware of it or not, functions surround us, shaping the world we live in. From the trajectory of a basketball to the growth of a financial investment, functions are the hidden architects of our universe.